Okay, let's move on to the next part, which is part B, part 1. Oh, a bit of a misprint there, not to worry. We're supposed to consider the quadratic form, which we can establish using this. And we want to express this in terms of coordinates capital X, Y, and Z referred to its principal axes. So let's see how we do that. Well, we need to establish the coordinates. So we put those in a vector, and then a quadratic form can always be written like this. And so we take the quadratic form we have above, and we calculate the elements of the matrix A, and we can do that using this. And we can see that this is actually the same matrix as in the first part. So we know that the equation of the quadratic form referred to the principal axes is just the quadratic where the coefficients are the eigenvalues of the matrix. So that's okay. So the next part is find an orthogonal matrix such that our coordinate vector is equal to some matrix P, which we're about to find, times the coordinate vector relative to the principal axes. So let's look at that solution. So such a matrix is actually the its rows consist of the the columns consist of the eigenvectors of the matrix A, normalized. So let's do that, and we can visualize this matrix using that. And we can see that it's orthogonal by multiplying it by its transpose. And the result is the unit matrix, you can see here. So we define a vector capital R relative to the principal axes, and whose components are that. And then we take the product of the matrix P with this vector, which is so, and the rule for transforming from the coordinates x, y, z to the original ones can be established using. So we take the coordinate number j and set it equal to the jth element of that, gives you that, and we apply that to the quadratic form, and we can see that that is the same quadratic form we got above, namely the squares of the coordinates relative to the principal axes multiplied by the eigenvalues. Well, that's all very good, and now we want to find the shortest distance from the origin to the original surface. So let's do that. So the square of the distance between the origin and a point with coordinates x, y, z on the surface is just this. And this can be expressed in terms of the new coordinates as this. So R transpose R is equal to, or little r is PR. We take the transpose and then we multiply that by PR, and using the rules for the transposes we can see that the result is R transpose R. So we don't have to worry about this. We can work with the square of the distance relative to the principal axes. So now what we really have now is a constrained optimization problem. So our object function is the square of the distance, and that has to be done such that the quadratic form, which is back here somewhere, is 0. So let's do that. And so that's the objective, or the Lagrangian, and we can differentiate that with respect to the coordinates using this. And this is the result. So we can see that there are 3 fairly simple equations, and either well, one of 2 things happens for each one. Either well, let's suppose x is 0, then this is automatically satisfied, and this gives an equation for lambda, and then this gives an equation for z, which will give z equals 0. So and so on. So let's take the first solution. So we could assume that x is not equal to 0. So we can solve, set the derivative of the Lagrange function equal to 0 and solve for lambda. And that gives lambda equals -1. And we put that into the derivative of the Lagrange function, and we can see that if in that event y has to be 0 and z has to be 0. So an equation for x can be found using setting those things in the quadratic form, and we can see that the solution to that is x squared equals 16, so x is plus or minus 4, and the answer is probably +4. And now to get the second solution, if we go back and look at the equations, then we can assume that y is not equal to 0 and set this equation equal to 0 and solve for lambda. So we do that, and we find lambda equals 1/4 for this case, and in which case if we put that back into the derivatives of the Lagrange function, we can see that they're this and this, and of course the solutions are that x equals 0 and z equals 0. And then we can get an equation for y using this, and find that this thing is always negative, so there are no solutions that come out of this case. And then finally we go to the third one. So we assume z is not equal to 0, and we look at the third component of the derivative of the Lagrange function, and we set that equal to 0 and solve for lambda. That gives lambda equals -1/3, and then the equations become, and we can see that in this event the solutions are that x equals 0 and y equals 0. And then an equation for the value of z, better change that, can then be found using this by setting x equal to 0, and we can see that that's an equation for z, which we can solve using this. And since this value is less than the first one, we can conclude that the shortest distance from the origin is this. And then finally, which is the correct answer, and then finally we can visualize this surface, if you like, using this to express z as a function of x and y, and then we can plot that function using this. And that's what it looks like. And if I now grab this surface here and rotate it, then you can see that this here is actually the minimum distance of the surface from the origin. The other possibility is this one here, which is clearly bigger, and then the final one is in the other direction. There is going to be no solution. So let's stop that